Hello, students. This brief overview will talk to you about the vapor pressure of solutions. Remember that solutions are homogeneous mixtures, in that when the components come together, being mixtures, it means that the components retain their own original properties. However, the presence of the solute actually impacts the properties of the solvent, some of them. And one of the most important is how the presence of the solute affects the vapor pressure of the solvent, or what we interpret to be the vapor pressure of the solution. Let's talk about why this is so. Whenever you have pure solvent, it can do what it wants to do. For example, in the case of water, some of these are bumping into each other and some are gaining enough energy to become vapor. And then that vapor exerts a pressure, of course, upon the liquid that it vaporized from. But with the presence of a solute, the behavior of the solvent is restricted. Now, we definitely know that some of the solvent is going to be bound by its attraction to the solute. And just some of the solute is in the way. So if this water molecule gets enough energy to vaporize, well, it's going to have to move around this mass of solvation that has consumed some of the solvent with the solute. So the solute acts as kind of roadblocks within the solution, but most importantly, it reduces the amount of surface that's available for the solute to become vapor, for the solvent rather, to become vapor. So that's the greatest hindrance, really, is the reduction of the surface because of the presence of the solute. So less vapor will be able to be formed, therefore, and thereby lowering the vapor pressure. In fact, as the mole fraction of the solvent decreases, so here's a graph that shows us the relationship of the vapor pressure of the solution, which, if we have a non-volatile solute, it's only the solvent that's creating vapor. So when we say the vapor pressure of the solution, we really mean the vapor pressure of the solvent. But as the mole fraction of the solvent decreases, meaning we have more and more and more solute present, well, the vapor pressure will continue to go down. So obviously, if we don't have any solvent there, if it's non-volatile solute, there's no vapor pressure. And then we gradually, as we get more and more and more dilute, or less and less solute, we originally reach a point with the mole fraction of solvent being 1, where the vapor pressure of the solution would be the vapor pressure of the solvent. Now, we actually have Raoult's law, which allows us to see the impact of the presence of the solute. Raoult's law is the vapor pressure of the solution is equal to the mole fraction of the solvent times the pure or initial vapor pressure of the solvent. And I have an example worked out here. So if you want to pause and you can read the example, look through my work, it's just really making sure that you have the mole fraction of the water times its pure vapor pressure at the given temperature. We understand, of course, that mole fraction does not have a unit, so you're seeing the fractional impact upon the pure vapor pressure. It is inconsequential what the pressure units are in. Just, of course, whatever pressure unit you're given, that will be the pressure unit that will end up being the unit for the partial pressure of the solution. And here is an example that is our first exposure to really what colligative properties are. The vapor pressure is lowered by the presence of the solute, but the number of solute particles is really important. Now, in this previous example, we were dealing with table sugar, which is molecular, which does not dissociate upon creation of the solution. So for every 1 sucrose, we get 1 particle in solution. So that's why we could just take, from our grams and interpret into moles to get our mole fraction. However, in this next example, I'm giving you sodium sulfate. Sodium sulfate, of course, being a soluble compound, will break into ions in solution. So we get 2 sodium ions, 1 sulfate, which gives us a total of 3 ions. So when we are calculating the mole fraction of the water, we actually have to look at the impact of 3 moles of ions. So we're not just looking at moles of our solute, we actually need to look at moles of our ions here. So please pause, take a look at just how this situation changes. So it's very important for us to be able to realize what kind of solute we have and how that solute is existing in solution. Again, I encourage you so much to always be able to visualize and really use your imaginations. So we have to be able to key in if we have an ionic solute or a molecular solute. All right, I'm sure that you remember with gases dealing with ideal gases and real gases. Well, with solutions, we have what are called ideal and non-ideal. So it's the same kind of idea. Remember, an ideal gas followed and obeyed all the postulates of the kinetic molecular theory and obeyed perfectly all of our gas laws. Well, an ideal solution perfectly obeys Raoult's law. So whatever the mole fraction of the solvent times its pure vapor pressure will give the partial pressure of the vapor pressure of the solution. However, if the solute and solvent either very, very well agree and really form a strong attraction, we're going to deviate from Raoult's law. And if they don't really get along, for example, if we have a polar and a nonpolar, that's going to deviate. Now first, a negative deviation from Raoult's law means the vapor pressure of the solution is less than what we would expect it to be. A negative deviation is a situation in which the partial pressure of the solution is less than what we would expect it to be. Where a positive deviation is a greater vapor pressure of the solution than what we would expect. And the situation is this. Whenever the energetics, the enthalpy of the solution is close to 0, meaning we don't get a lot of heat released or absorbed when the solution is formed, that's going to give us the situation where Raoult's law is perfectly obeyed. And that happens in a lot of cases. However, in the case of acetone and water, we can have hydrogen bonding between the water and between the acetone. So these guys very, very, very strongly attract each other. So in that third term, when we allow these guys to form the attraction for our solution, that releases a ton of energy, a ton. So these guys are really, really going to attract each other. So we are not going to release as much water as vapor or acetone as vapor. And so the vapor pressure for the solution will be lower than we expect. In the case of hexane, which is nonpolar, and water, which is polar, these guys really don't get along too well. So they are actually going to have a higher tendency to move away and create more vapor. So in the case where your solute and solvent really don't have any attraction, you could possibly create more vapor and you have a greater vapor pressure that is calculated, or that is seen, that is calculated. I have an example here that gives a situation, gives you what the vapor pressure is measured to be. And so what you're asked is, given the amount of acetone and the amount of chloroform that you are using to make a solution, it's saying if the vapor pressure is measured to be 260 torr, is it ideal? So what we have to do is actually calculate what Raoult's law would predict, compare it to what is experimentally seen. If it matches, it's ideal. If it is greater, then there is a positive deviation. If it's less than, there's a negative deviation, and then it's a non-ideal situation. Now, whenever you have two liquid components, so you have a liquid solute and liquid solvent, that's when we're going to look at modifying Raoult's law. And so we know that there's two things that are creating vapor pressure. So in the case of the next problem, we want to look at the mole fraction of acetone times the pure acetone vapor pressure plus the mole fraction of the chloroform times the vapor pressure of the pure chloroform. So if you take a look at what I've done, I first got moles of the acetone and then moles of the chloroform, got the mole fraction of each, and then to get total pressure, looked and added each term. Now, depending upon how you adjust your sig figs, you'll get 319 torr or 318 torr. Now, the actual is 260, so what is expected is 319. So that means that those two components are attracting each other greatly, so we actually are getting less vapor out than we would expect. So this is a negative deviation. I have some real world examples here. Your book really nicely illustrates this. Let me just let them come up. Now, whenever you have ethanol in water, for example, that's going to give you a negative deviation. Oh, I'm so sorry. No, as it's reading here is a positive deviation, where ethanol and benzene would be a negative deviation. Or is that what we're, yeah. And we will see more examples of this in class. Just going back to this last example. Okay, best of luck.